All right, let's go ahead and get started. Hello, everyone, and welcome to our webinar, Advancing Clinical Imaging with AI, Integrating NVIDIA Clara Models into VolView. I'm Andinet Enquobahrie. I'm a director here in the medical computing team at Kitware. I'm joined today by Andrew Howe, one of the VolView core developers. And Andrew will be showing a demo of the software and discuss how we can customize VolView for different applications. Just before we get started, I'd like to mention a couple of logistics. We will make the slides available after the webinar, and also the video recording of the webinar will be posted to our YouTube channel. So you'll be able to watch it again and also share it with your friends and colleagues. We do have a Q&A panel, so anytime if you have any questions, please post your questions. We don't have to wait until at the very end. We can just grab them as they come and we'll be able to answer them. And also there's a chat in a feature in the webinar. If you would like to say hello and connect with other attendees, please do so. All right. So last week was a very exciting time where NVIDIA hosted their semi-annual conference in Washington, D.C., GTC conference, where they brought together leaders from a lot of different areas, government, healthcare, research, industry, and it covered a wide range of sectors. But one of the key highlights of this conference was a keynote speech by Kimberly Paul, NVIDIA's Vice President of Healthcare and Life Science. In her presentation, she talked about how multimodal AI is reshaping clinical workflows. In fact, as part of this keynote speech, she announced the release of new NVIDIA Clara Open Source models that you can use for segmentation, reasoning, and image generation. And these open source models are being started to integrated into other platforms. Obviously, we're very excited that she mentioned Kitware at her keynote speech and talked about how these open source Clara models have been integrated into VolView. So we wanted to build on that momentum of this open source model release at GTC and bringing together open source AI models from NVIDIA, open platforms from Kitware like VolView, and then we want to talk about a little bit how you can use VolView in your product development, your research, or relevant effort. Great. So what are we going to be covering today? First, we'll talk about what's VolView, what's its design principle, what's the underlying technology, who is it meant for. So we'll go over some high-level description of VolView. Then the next part will cover why we wanted to integrate AI models into VolView. So what's the motivation behind integrating open source AI models like Clara into VolView? Then, people would be interested in customizing VolView for different applications. So we'll do a walkthrough of the architecture of VolView, like how are the underlying data handling, visualization, and then AI services come together. And then we'll go over what are the key use cases of this new AI integration into VolView. And this will be followed by a live demo by Andrew. And then also after the live demo, Andrew will talk about, all right, how can you take VolView, customize it, and adapt it for your own specific needs, whether it is adding and integrating new types of AI models or extending the module panels and adding some new visualization and analysis techniques. And then something we've heard from our collaborators and customers is how can you then take VolView and deploy it on the cloud? So we'll spend a few minutes talking about what are some of the best practices deploying VolView in the cloud. And then obviously at the end, we'll wrap up with a summary, next steps, and then we will make sure to have leave time for some question and answer session. Excellent. So, that's been the plan for today. So, kind of to set the stage a little bit, and also because we will be talking about VolView, which is really built on decades of open source innovation and collaboration across different teams at Kitware. I want to talk a little bit about Kitware. So Kitware is a leading provider of software and AI and R&D services, and we work with different types of customers, government, industry, academia. Obviously, work a lot in medical imaging, but besides medical imaging, we work in scientific computing, high performance software, and data solution. So our company is about 200 employees with 6 offices in the United States and Europe. We'll spend today's webinar focused on VolView, but beside VolView, Kitware leads the development of a wide range of open source tools. You might know some of the ones that are shown here. CMake is a very widely used cross-platform build system for C++ software configuration, build, and management. VTK and ParaView, they are industry-leading visualization tools. And then we do have several other tools like Pulse for physiological simulation, VIME, and Quiver, that's led by the computer vision team. So we use all these open source platforms and to develop applications for researchers, government agencies, and industry professionals worldwide. All right, so before we dive into the main part of our presentation, we would love to hear from you, the attendees. So here we have our first poll question. So the question is, what best describes your role or background? So we've given you 5 choices: clinician, researcher, software engineer, healthcare administrator, or a student. So please take a moment to respond to this poll, and then we'll continue with our presentation. Great. So we thank you for participating. So the majority of the participants today are researchers and scientists. All right. Great. Thank you. All right. So what's VolView? So VolView is it's a web native imaging viewer, right? And you know, there are other types of viewers out there. What's very exciting about VolView is you can do all the rendering right in your browser. So you don't need a very beefy, heavy workstation, but you can just do rendering within your browser. So it's a client-side rendering library. It's built using very popular open source software, VTK, Visualization Toolkit, ITK, the Insight Toolkit for segmentation registration, and also other modern web technologies, graphics technology, WebGL and WebGPU. So this will allow VolView to be able to provide fast, interactive 2D and 3D visualization directly on your browser. It has all the basic standard radiological operations and measurements like annotation, windowing, and Andrew will be demonstrating some of this. But besides these standard radiological functions, VolView has a way of doing 3D cinematic rendering. So the cinematic volume rendering generates this very beautiful rendering that researchers and also clinicians use for a couple of reasons. One, for patient education and patient communication, but also for training of radiologists. You can just drag and drop DICOM data in a DICOM format or other types of medical image data into your browser to be able to do your visualization. And then the best part is you can just go straight to volview.kitware.com, and we do have a free hosted version there that you can start using VolView. VolView comes with some sample data set that's bundled with it. So you'll be able to just click on one of the sample data, visualize it, and interact with it. But of course, we'll be showing a live demo of VolView, and then we'll show you how the different components function. Great. So why we are interested in integrating AI into VolView, right? What's the what's driving this integration? And the answer is related to the complexity of medical image data in the radiological community. I mean, there's the amount of data that's being generated is exploding. There's a whole complexity of different types of modalities, and that requires some help or automation. And as you know, healthcare makes up more than 30% of all the data that's generated in the world. And then medical imaging specifically makes up 80% of all healthcare data. So it's a huge amount of data. So this necessitates AI automation. And then modern AI models can really help radiologists by looking at helping with segmentation, triaging, detecting some tumors, anomaly detection, reasoning about the different findings. All these tasks are very repetitive, and having an AI tool would make it very useful. And also, one of the reasons we're very excited about these NVIDIA Clara AI models integrated into VolView is rather than having a separate workstation or a separate application where you can run your AI models, you can run your AI models within VolView. So you have this integrated application for starting from loading your data, doing some pre-processing, running your AI model, then reviewing and inspecting your AI results in one unified application. So as I mentioned at the beginning, one of the biggest developments that came out of the GTC conference last week was the release of these open source models. These are Clara medical imaging open source models, and these are foundation models that you could use for segmenting different structures. You can use Clara open source segment models for looking at, outlining borders of organs and tumors and different anatomical structures. You can use these models for doing interpretation of image finding. And we're actually going to show how you could do this using chest X-ray. And also, you can use these open source models for generating some new synthetic CT and MRI data. And generation of this realistic CT and MRI data make it very, very useful for machine learning training, simulation, and also other types of algorithm development. All these models are open source. So you can go to GitHub, NVIDIA MedTech, where you can have access, you can be able to see, I have access to these models. All these models are built on top of MONAI, which I'll talk about in a minute. So the fact that these models are available open source, they're also, by the way, available as part of the Hugging Face NVIDIA collection account. So you can be able to check it out from there. The fact that these are open source that can then be used, then you can use them to integrate it with other platforms like VolView. So these Clara models are built using MONAI, and I think folks who are working in the medical imaging AI or medical image analysis know MONAI. I'm sure they know MONAI because it's become sort of the de facto open source PyTorch framework for doing deep learning in medical imaging. The great thing about MONAI is it helps you do end-to-end pipeline setup. You could do data loading, you could do augmentation of your data, you could do model training, inference, deployment, and all different types of models. So it's purpose built for medical imaging. It has all these customized components that makes it very useful for medical imaging. And again, it's open source. You can check out the project on GitHub. Just to give you a sense of the scale and impact of MONAI, which was incredible, and this was also shown at the keynote speech by Kimberly Paul at GTC. MONAI has now over 7 million downloads. So that shows you sort of the level of adoption. And it's also deeply embedded in the research community. You know, as you can see, thousands of peer-reviewed papers that reference MONAI has been published. Also, MONAI has been used in several grand challenges. For example, in MONAI, where it's been winning a lot of those grand challenges. Teams who participated in the grand challenges used MONAI to be able to build their models and participate. And more than 20 grand challenges were won by a team that's using MONAI. The MONAI model zoo has become a very rich source of pre-trained models. The last time I looked at it, it's got more than 40 pre-trained models that you can, and this includes segmentation, classification, detection. So you know, for example, you're interested working in liver lesion segmentation, you'll be able to go in there and find a particular model and use it. Also, the community is growing. So more than 200 researchers and developers have made contributions to MONAI. So it has, and also besides these active contributors, thousands of active users are using MONAI for their research, application development, and product development. All right, now it's time for our second poll question. Before we dive into some of the AI model description, we want to get a sense of your familiarity with AI. So if you can take us a minute to answer this question, how familiar are you with AI for medical imaging? And then we've given you 5 choices. So take a moment to respond to the poll question. Great, thank you. So the majority, more than 60%, of you are just getting started and learning basics. And that's, you know, the great thing about open source software and open models. So you'll be able to check out the software that we will show you and also the open source models, and you'll be able to learn from it. So that's great. Yeah, thank you for participating. All right, so next let's go over the architecture of VolView. So VolView is designed in a way it has 3 main components. The data ingestion, data source component, the front end, and the back end. So in the data source, you're basically looking at bringing in your data, and there are VolView allows you to be able to ingest data in 3 different ways. One is you can connect to a PAC system, a picture archiving communication system, and be able to query and ingest data. The data could be in your local file, so you can use your local file to be able to load data directly to VolView. And also, if you have data that is stored in the S3 buckets or some cloud storage, you'll be able to directly use that to ingest data into VolView. Next, we have the VolView front end. So this is basically your application in the browser. And we'll see a demo of this in action. So this was basically where the users spend a lot of time, where you are visualizing the data, you're looking at different layouts, you're doing annotation, you're generating segmentation models. So all this is happening on the client side. When you're interacting with your data in the browser, your data remains in your browser. Next, we have, and again, just to summarize, the front end would allow you to ingest data, visualize, and do some annotation and segmentation. All right. So whenever then you need to be able, if you're interested in doing some AI processing computation, or you need some have tasks that require high computation, then you can use the using the available web API to communicate with your backend server. And then we will show how we're going to use VolView's backend server architecture to be able to run those AI services that are made possible using NVIDIA's Clara open source models. And this backend server would allow you to be able to do use distributed computing, right? For example, if you have a segmentation task that's going to require a lot of GPU, you can run it in one server, but then you can then do your synthetic data generation in a different server. So you'll be able to distribute the computational task. Also, the backend server is where we're doing all our AI model inference. So that's where we'll be calling the Clara open source model and running them around input data. And then I'll talk a little bit about this, where you are able to deploy your backend server on the cloud, where you can have access to scalable resources as well. So this type of architecture will allow you to be able to run the front end on your own local browser, but the backend server can be run on a remote server. All right. Just to summarize, this architecture would allow you to be able to have this application that is browser-based. You have both visualization and AI, scalable AI workflow together. Visualization of the data and processing remains on the front end. And then the backend has this extendable architecture where you can run these microservices on different computers. And then the AI layer, you're bringing in these AI models using MONAI, PyTorch, NVIDIA Clara. That's going to be run on the backend server. So all in all, this gives you sort of a unified architecture where you could do data access, visualization, and AI task inference together within one unified application. All right, so this one's a little bit more detailed architectural diagram. I'm not going to spend a lot of time on it, but I want to just highlight some key components here. So as you can see here on the front end, we do have the core technologies used in VolView. We're using VTK.js. This is a visualization toolkit, JavaScript library for doing the 3D rendering. The cinematic rendering, all that stuff is done using VTK.js. We're using ITK WASM. So that's a WebAssembly compilation of ITK for handling the imaging data, because ITK has a very rich set of readers for different types of medical image data formats. So we're using ITK WASM for that, and also doing some pre-processing of the data before visualization, or even before we sending it off to the AI pipeline. Now, there will be 3 panels that we will be focusing a lot during the demo. And these are, we'll call them user interface tabs for doing segmentation, reasoning, and generation, right? These are dedicated user interface tabs that we use to do those three services. And obviously, as I mentioned earlier, when we run those AI services, they're going to be sent through a lightweight WebSocket communication into the backend server. And the backend server will have access to 3 services, and this can be all run on the same server or different servers. And Andrew will demonstrate this. So right now, if you look at the demo we have for GTC, we've got 3 servers set up. One for doing synthetic data generation, generate server, which is going to be calling on the NVIDIA NV segment CT model, and they do have also MRI model. And then we have as a chat server where you have this conversational AI with chest X-ray. So the model that was released only focuses on chest X-ray, and I know they have plans to release additional LLM models as well. And then the third one is segment service or curate service. So once you have the data loaded, you select the data and you run the segmentation, you'll be able to run the segmentation and be able to identify different structures. So the reason we designed VolView in this particular way is for a few reasons. One, having this distributed design allows us to have a more scalable microservices, right? For example, the chat service that's running can be run on a different different server. So this allows us to do this, scalable microservices. Now we're using WebSocket communication, which means you'll be able to have a real-time updates coming in. All right. When you are running the chat server, if you run into some issues, the whole system is not going to come down. It's still the other parts of the application is going to continue to function. For example, if your chat server is failing, your segment and generate server will still be functioning. So it has a good way of handling those type of issues. So it has some resilience designed into the system. It's cross-platform, obviously, because it's a browser-based application. So whether you are on your Mac, your Unix, or Windows, whether you're in Firefox, Chrome, or Safari, you'll be able to use it, right? And then, as I mentioned earlier, there are multiple ways of bringing data into the system, into your application, either connecting with a PAC system, or from a cloud storage, or from your local your local file. Again, at the end, just in summary, VolView architecture allows you to have this unified system of AI, visualization, and data handling. All right. So next, I'll just quickly go over some of the use cases, and then I'm going to hand it over to Andrew to see the demo, which is actually obviously the more exciting part of the webinar. By the way, if you have any questions, please post it on the Q&A feature, and we'll be able to get to them. Are there any questions so far, Andrew?
Nope, at the moment, nobody's asked a question.
Okay, yeah. All right, so let's just quickly go over 3 different use cases of VolView with NVIDIA Clara integration. So the first one is synthetic image generation. And again, here we're talking about very, very realistic, anatomically consistent synthetic CT and MRI data. So these are not, toy images that kind of look and feel and behave like real medical data, but they're actually very high fidelity, realistic synthetic scans. And why is this so important? Well, when you're working on training a new AI model, you are usually you need access to high quality data sets, because obviously in medical imaging, there's issues with HIPAA compliance, privacy is a big issue, and also depending on the type of data and type of modality and type of organ you're targeting, getting access to that particular type of data can be very, very challenging. So a way to generate synthetic data is very, very powerful, especially for researchers. And then another use of this synthetic data generation is education. Like if you're training radiologists in the medical school, or even as a radiology techs, you'll be able to generate different types of synthetic data, and you can use those synthetic data for your as part of your educational curriculum, right? So VolView, and as Andrew will demonstrate, allows you to talk to the generate server, and then also basically set up a way to generate CT scans based on your prescribed protocol. In this particular case, the size of the data, and then the slice thick, the XY resolution, and the slice thickness. And the second use case that we'll be demonstrating today will be segmentation, right? So obviously, in any medical imaging task, being able to identify the organs, isolating tumors, measuring volumes, outlining region of interest. These are all very, very important tasks, right? Because segmentation would allow you to identify the pixels that are so important for your clinical interpretation. So NVIDIA has released segmentation models for CT and MRI. And this was, I mean, originally what's called the Vista 3D. Vista 3D model. It was only CT scan, but last week they also released a segmentation model for MRI. So you'll be able to load a CT scan or an MRI scan and then be able to segment all the different organs. And that's what you see here on the screenshot on the right is for segmentation.
Andinet, a question
Yes,
came in.
sure.
As a surgical oncologist, the question asked was, will this model help me to plan organ resection?
Yes, so that's a very good question. So let's say just for the sake of discussion, you're looking at doing liver tumor resection. So, and I imagine as part of surgical procedures, you'll be acquiring some preoperative imaging, right? Let's take MRI or CT scan. So you can load it to VolView and you can say, go liver segmentation. And actually, Andrew will be able to demonstrate this later on. Then you can segment the liver. And then you have now your liver model. Now, you'll be able to then do your planning of the surgery based on that identified model. I'm sure you'll be interested in, okay, what orientation direction should I be inserting my instruments? How large should be the surgical margin around the liver tumor? All these things you'll be able to do. So yes, so you'll be able to, it's a very, in fact, segmentation is obviously one of the critical pre-processing tasks involved in surgical planning. So yes, so VolView will help you in your surgical planning tasks. Any other questions, Andrew?
Nope, no other questions.
All right. And then just quickly to wrap up the use cases, the last one is something that's also becoming very critical, is this aspect of reasoning, right? So can you be able to provide the AI models with the imaging data plus some additional textual context information? It could be clinical information. And then will you be able to do some conversation, Q&A? And that's what Andrew is going to be demonstrating, is you can actually load a chest X-ray and be able to converse with it using this reasoning chain of thought AI model. And this has been released last week. So this chest X-ray multimodal AI model was released last week, and then we'll be able to demonstrate that. All right. With that, I'll hand it over to Andrew for a demo.
Okay. So right now I have open the version of VolView that was previewed at NVIDIA GTC DC, and this has the integration with the 3 Clara models that were released. But before I go into those, I want to first give a quick introduction into how to use VolView generally speaking. So VolView as a radiology or radiological viewer supports a lot of supports several imaging data types. So for instance, because we use ITK WASM, we support NERD or NIFTY files, and there's the sample data here, which you can just click on to download. You click on any one of them and it downloads them from Kitware server where we're hosting the sample data. But in addition to being able to load data like this, you can also open files in the local file system, or you can drag and drop. So I have a few examples here, like this NERD file, and this allows you to very quickly input your data if you just want to rapid analysis, or if you're just trying something out. Again, you can try this out on Kitware's open demo. Another thing you can do is you can configure a PAX endpoint, or DICOM web endpoint, where you're hosting a server that is storing the DICOM images, and they can very quickly be transmitted to the VolView app via DICOM web. So I'm running this app in my browser, and as a browser-based app, as Andinet said, any device that implements a browser can display the VolView app. So it's very portable and very user-friendly. So now I want to go into some of the controls here. So these are the radiological controls, and you can set things like the layout. So you can just look at the axial axis, or you can look at the quad view, which shows the 3D, as well as the coronal, sagittal, and axial axes. So another thing that you can do is you can set the window level, so window and level. So if you drag vertically, you can change the window size, and then if you drag horizontally, you can change the level. So this is these are just common functions that you might want to perform on radiological data. You have these presets that are just predefined window and level settings that happen to visualize certain features very easily. So we have bones here. You have air, soft tissue, lungs. These are just affecting the window and level, and it's not always perfect, but they're just presets. So another feature that we have here is you have these basic controls, like you can pan, you can zoom, and then you have these crosshairs. And what crosshairs allow you to do is set the slice in two other. You can by interacting with one of the axes, you can set the slice of the other two axes. And so, for instance, if you want to look at the kidney, you might be interested in visualizing it. You might be interested in visualizing the slices of a kidney on the sagittal plane, but you're wanting to create that visualization from the coronal plane, which I'm doing right now. So we also have these annotations and segmentation features. So if I go to annotations, and sometimes the tab bar up here is a little finicky, but right now it's doing fine. So if I go to paint, I can start creating a segmentation. So I can change the size of the brush, and maybe I want to get the kidney. I'm not really perfect, but so this is just for one slice. So you can flip through the slices, and you can segment slice by slice. You also have these different. You can create different segment groups. You can edit the color. You can show and hide different segment groups, and you can also save segment groups. So if I save this, I might want to export this and share it. And for each of the segment groups, you can also parameterize the fill opacity, outline opacity, and the thickness. We also provide this measurement feature. So, for instance, a rectangle is where you define 2 points, and it creates a rectangle as a measurement where it records the slice and the axis on which you made that rectangle. The same goes with the polygon. Yeah, it just switches to the segment. That's just a quirk right now. But you can create a polygon, and again, you can set things like you can set its visibility. And then you can also use the ruler feature, which is useful if you might want to measure the size of a tumor or a certain part of an organ, and that creates a measurement. And then if you flip through the slices, you can easily reveal that slice by clicking on it. And since these are all in the same plane, you're going to just see it all when I click on one of them. But you might want to flip through them. Okay, so another feature I want to go over is the volume rendering. So just briefly, you can set the opacity function here. So you have the histogram, and then you have the opacity function. You can play with the shift and width, and then we also offer a cinematic rendering in VolView, which I'm not going to go too much into because these are more advanced features that you might want to view other webinars or look at the documentation before going into that. So. Oh, one more thing you can do is you can crop. So you can easily crop a 3D volume from either the slices, or you can choose an anchor point on the 3D, and you can also like double click it. sorry, you can expand 3D, and you can easily crop like this by selecting an anchor point. After you've done your image processing, you can save your session, and that will save all of the data that you've input in this session into a file that you can easily load into VolView, or you can export, and you can use that to export images. So now that I've shown these features that are native to VolView, I want to go into some of the models that we've integrated, and what we feature with them. So I'm just going to refresh to reload it so I can have a fresh set of data. I don't want to have all the other data that I was just messing with in. So the first thing I want to show is the generate model. And actually, before I show that, I want to quickly show what I'm doing here with how these models are being run. So as Andinet said, we have a distributed architecture where you have multiple Python servers that are accepting these requests to generate data or segment a data set. And there's a WebSocket connection being made remotely, and a function call is created by RPC, which is remote procedure call. And so when you want to generate a 3D CT, we have a server running a Python instance that will receive the parameters. It'll generate the CT and send it back to the client over the WebSocket. And actually, in our case, we're connected to two different computers. So for the segment server, I'm connected to a server that has some GPUs in it. For the reasoning server, which is the chat, we're also connected to the same computer. But then for the generate server, we're connected to a separate one. Andinet will go over this more in detail later, but you can imagine that you might want to have a scalable cloud instance or connect to a proxy. And by doing that, you would be able to leverage very, very powerful models, or you might hook VolView into a training routine. There's a lot of capabilities you have with this distributed architecture. So I'm going to choose a 256 by 256 by 256 3D CT, and hopefully it works. It's running on one of our backend servers, and you can see that it's accepted the parameters, and it's right now using up some GPU memory, but it's right now generating the CT, and hopefully in some due time it comes back. There's a lot of utilities to generating to be able to generate data, especially 3D CT data. So for instance, you can use it to train other kinds of models. Like you might have, I wouldn't suppose you would want to use a generation model to train a generation model, but you can maybe create data for classification, or you might be able to create data to train a segmentation model. Another thing you might want to do is, in some cases, you might have a patient that has an MRI and you want to generate a CT from that, reducing their radiation exposure and saving a tremendous amount of time and money. So anyway, so you have now a 3D CT scan. This was generated by the NV Generate CT. And for all these models, we also have this model card here, which is it's a feature that was popularized by MONAI, where it specifies the underlying machine learning model, as well as some recommended parameters, sometimes how the model was trained. It's mainly for transparency in the AI community, and these model cards are available for all the models we've integrated. Excuse me. Okay, so that's the 3D image CT generation. So now there's the segmentation. I could run a segmentation on this, but because I'm not sure about some of the organs on this being very high fidelity, and because I chose a very low resolution due to the limitations of our cluster, I'm going to drag and drop a different piece of data. So this very high fidelity large nerd file. Okay, so for NV segment CT, you can choose a set of organs that you want to segment, and it will, and just like with the generate server, it'll send the image as well as the parameters to the backend server. It'll perform the segmentation and send it back. So in this case, we can do kidney and maybe pancreas. I'm pretty sure I've chosen these combinations before, but this is truly ad hoc. You can do whatever. You can segment anything, and I think it's really incredible that we can have a AI model do the segmentation, because Manual anatomical segmentation, especially of multiple slices, can take a physician dozens or a clinician dozens of minutes. And because it's so time consuming, therefore it incurs a lot of, there's a high cost, there's a time cost associated with that. So with something like this, though, you can have an AI model do the segmentation, and maybe it gets it 95% right, but it gets it done in 10 seconds. And from that, you can adjust to the segmentation. You see, if I go here to annotations, it's now a segment group that you can select, and it's labeled, and you can edit the segmentation using the paintbrush, and that's highly beneficial for being able to adjust the results. And because this is all, we've just sort of put this together when NVIDIA released their models, there's a lot of ways that we can just change or swap out the model, and we can also add new features that are in development, like adjusting what the model is segmenting based on a point. So you can select a point and say, that wasn't right, that wasn't supposed to be the kidney, that was supposed to be the liver, and then it would adjust that segmentation. So all of these features in medical AI are currently emerging with newer models, and we're excited to show these in VolView. The last one I want to show is a reasoning model. And this is the NV Reason CXR 3B, which is, I think, a fine-tuned version of Qwen, and it works on 2D chest x-rays. So I'm going to actually drag and drop a 2D chest x-ray instead, because this doesn't work on 3D data, and it only has an axial slice. So I'm going to make sure we can only see the axial. And from this, you can ask it questions. So I can say, examine the chest x-ray, and just like before, it sends the prompt as well as the image to the back end. And the usage for a reasoning model, just like the others, is these are really state-of-the-art developments, and we're able to run them in VolView because of the distributed Python backend. And these developments are, making their way into a lot of research and clinical research use cases, because they can provide physicians with a resource for querying a patient's case, or you can have researchers who are not, they don't know everything about chest x-ray. They can ask questions, they can interact, and the model will take all of the data as well as the prompt, and it will give an answer that may have been, it might have been useful for the patients, for understanding the patient's case. So here's a response. It's quite long, and this is NVIDIA's model. A few weeks ago, we actually showed this with MedGemma, where we integrated Google's MedGemma multimodal language model, and the responses were very different. So you can fine tune these models as their foundation models. They're intended to be fine tuned. I can say, do you see any signs of, actually, do you see any abnormalities? So yeah, this is the reasoning model, and these were all these features were demonstrated recently in the NVIDIA GTC conference. So let's see what it says here, and then I'm going to hand it over back to Andinet. Okay, yeah, so it responds. This response is showing a think token as well as the answer, but that's how the model that NVIDIA trained behaves. And we can also make modifications on our end with that. For instance, we can remove the think token, or we can do some extra processing of the prompt. These are all things that you're able to do very quickly and easily due to VolView's extensibility. Okay.
Hey, Andrew, you want to go with the next poll question and customization?
Yes, let me reshare my screen.
Sure.
Okay. All right. So just a second, just skipping forward. Okay. Yeah, so we have another poll question. Which area of Clara model integration into VolView excites you the most? And the choices are segmentation, automated organ and tumor labeling, reasoning, conversational AI and decision support, generation, synthetic data creation and augmentation, architecture, open extensible microservice framework, or clinical workflow integration. So streamlining image review and reporting. And feel free to go over the results, Andinet.
Sure. Yep, they're coming in. Yeah, it looks like the majority are saying the segmentation, the automated organ tumor labeling would be that something they would be interested in. And the next, the second one is on reasoning, conversational AI and decision support. Great. All right.
Okay.
Thank you for participating in the poll.
Yep. And I also briefly want to touch upon customization, which we've sort of went over a bit, but just to get these things clear. So one of the biggest strengths of VolView is just the fact that it's so customizable. So everything you've seen so far, the viewer, the AI integration, the workflows are built so organizations can tailor it to their needs. We really quickly set up this integration with NVIDIA's Clara models, just like we did with Google's MedGemma. And our goal is to really increase the speed of iteration for a lot of these, for integrating these AI models into actual applications, because we have these very easily configurable endpoints. And VolView is open sourced. It's an open modular platform. So it means you can add your own data sources, plug in your own AI models, and shape the user experience as it fits. So another thing is, if you've already trained AI models such as segmentation networks, classifiers, detection models, or even your own multimodal models, you can drop them into the service layer that we showed. And so that's what we've done. You can also, another thing is that you can customize workflows. So if your team needs a specialized segmentation review tool, or a structured reporting pipeline, or a research-specific UI tab, those can be added. And this is really important for institutions who are building internal AI ecosystems, or companies developing imaging products. So you can start with VolView as your foundation, then build up from there, your models, your logic, your branding, or your workflow. And then cloud deployment is next, and Andinet is going to go over some of that.
Great. Thank you, Andrew. Yeah, so I know we're kind of running out of time, so I'll try to go quickly through a few items that of interest to some of our customers and collaborators. The first one is, yes, this is fantastic, but how can we deploy it on the cloud, right? And I just want to spend, just half a minute to talk about what are the best practices here. So as you can tell, we have a distributed architecture with microservices. So what we propose and suggest is to be able to first containerize the backend services. You can have a container for segmentation, a container for reasoning and generate. And that way, having that containerized services will make it a lot easier. The other one is so just one second. There you go. So the other advantage here for deployment is, for your front end, obviously you want to have a production version, having once you build them, and then again you can serve your static assets, sort of web server or CDN, for faster access. With regards to the compute environment, again, having ways of containerizing the backend server and then using NVIDIA support will make it easier. One thing we haven't done yet, but it's so important, is, let's say you are running several segmentation tasks or generation tasks. How can you asynchronously scale up the resources available for all those different task executions or different sessions? Having a way of brokering the tasks versus the requesting sessions will be critical. Obviously, as using the generate service, we're generating a lot of medical image data, synthetic data. What's the right way of storing those data on the cloud? And the good thing is there's a lot of different options available to you, whether it's for compute or message brokering or containerization or even storage. I mean, if you're an AWS shop, you can be able to use EC2 instances, or you can use S3 buckets for storage. if you're a Google Cloud Platform shop, the Azure shop, you do have all these different options because all those different public cloud service providers have some offering for compute, message brokering, for containerization and storage. All right, just to wrap up, and hopefully we'll have a couple minutes for Q&A. What we showed today is a VolView that has advanced visualization and now has this integration with AI system. It's very extendable. You can use it for your research, your product development, and it supports, as we just showed, it supports segmentation, reasoning, and conversational AI, and also generating new images. The great thing is it's open source. I mean, anybody can access it. You can check out and I will give you some links and some contact information. You'll be able to check it out, take a look at it, use it in your project, and then be able to customize it as well, right? Some of the areas that we're planning to work on is add more support for other LLMs. And as Andrew mentioned, we've integrated MedGemma a while back, but there are other multimodal LLMs coming and being released, so we'll be integrating them. And then expansion of this multimodal support with AHR data as well. Adding features within VolView where you can have this collaboration. One of the researchers or clinicians could be doing segmentation and generation. We want to find a way to other collaborators be able to review what was done. And again, as we just talked about it, making it easier for cloud deployment. So just to wrap up, again, if today's presentation, webinar, and demo was very interesting to you, and if AI assisted imaging, multimodal workflows, and custom integration, that's something you're really interested, we just wanted to suggest some next steps. You can go to Kitware Medical Organization and GitHub, be able to clone the repository and then build it and run it on your machine. So that's actually the best way to give it a try. And then if you're curious about or interested in some extensive customization or integration of some new AI models, we'll be able to help. And Kitware, one of the things we do, obviously contributing to the open source community, is customers, collaborators interested in some custom software and cloud deployment will be able to help you with that as well. So, get in touch. You can use the QR code that we're showing here that will directly take you to our contact form, or you can just use the contact form to contact us, and we'll be able to help you with your projects. With that, I just want to see if there are any questions from the audience. So as I mentioned at the beginning, we will be making the slides and also the recorded video available to all the participants. You'll be receiving a follow-up email from our media team. Any questions? All right, I guess there are not any questions. So we thank you so much for joining us. Again, we really appreciate your interest, and look forward to seeing you in our next webinars. All right. Thank you. Bye-bye.